Okay, good morning, ladies and gentlemen. This is Professor David J. De Los Reyes. For this morning, I will be discussing a continuation of my long video format, DC circuit, and I am now on lesson number 14. Lesson number 14 will be an application of the so-called Norton's Theorem. So for this morning, I will be discussing an example problem and how to compute for the current on the certain part of the circuit by using Norton's theorem. Okay, let's proceed. This is a long video format topic. This is DC circuit lesson number 14. We are now on lesson number 14. And the title of the topic for this morning will be Norton's theorem, an example problem. To illustrate Norton's theorem, we will be solving the same problem as from the previous other concepts, like on the Thevenin's theorem. We solve a circuit there in which the current for a certain resistance there is actually the one we are looking for. So we will be solving that same problem, this one, by using Norton's theorem. Okay, let's try to bring out the figure. The figure will be the same as from the previous problem under Thevenin's. This is the figure. Okay. All values are the same. The voltages are the same. The problem is asking what will be the current passing through this 8 ohm load here. So for this morning, we'll be solving the current passing through this 8 ohm load here by using Norton's. Okay? So supposed to be, the answer from the Thevenin solution will be the same as for the solution for this morning. Okay? Let's try to bring out the figure. We got a 24 volt source here, and the resistances are this one. This is 2, 4, 6 ohm, 8 ohm, this is 10, and 12 ohm. And for this problem here, we are to look for the current passing through this 8 ohm load here by using Norton's theorem. So the requirement, find capital letter I with the subscript 8 ohm equal to using Norton's theorem. Okay, let's try to bring out the solution. There are actually 4 steps on how to, or 3 steps on how to bring out the solution. So step number 1, this was actually the summary of lesson number 13. That's the concept of Norton's theorem. Step number 1, we will disconnect the 8 ohm load, short the terminals, and solve for capital letter I with the subscript AC, meaning the short circuit current. So for step number 1, we'll try to disconnect the load. Load meaning the current and the resistance in which the current will be the one we are looking for. So we disconnect it, right? Then we try to short the terminal. Okay? We disconnect, then we short the terminal. So what comes out is actually this one here. Okay? We disconnect it here, then we put the shorting wire, and we must have to compute for this short circuit current here. Because Norton's theorem is actually a constant current source. So instead of voltage, the one we are looking here, because in the Thevenin's, we will be solving the open circuit voltage here, but for the Norton's, it will be the short circuit current. But before we could compute for the short circuit current, we must have to short the terminals. So if we try to short the terminals, this will be the configuration, right? We remove the 8 ohm load for the meantime. So by using our knowledge on the concept of series parallel concepts, we'll try to solve for the short circuit current. So to solve for the short circuit current, we must have to compress all this resistance here. Okay, so we could solve for the total RT. Total RT. We try to compress this resistance here by using our knowledge of the concept of series parallel. And to do that, we start on the right side, right? This portion here. We don't start from the load side, we start from here. So if we try to inspect these 4 ohms and 12 ohms, we could take the single equivalent of that one. The current passing here and here are actually the same, so they are in series. So I place it here. Capital letter R with the subscript E1, meaning the single equivalent of these 2 here will be 4 plus 12. 4 plus 12. Right? And it will be 16 ohms. The single equivalent of this one will be 16 ohms. Okay? So it's just like we have here a resistance. We remove this one now and this one. Okay? And this is 16 ohms. Right? And if we try to compare the current passing through the 6 ohms and 16 ohms, they are actually, these 2 here are in parallel. So I will represent the single equivalent of 6 and 16 to be RE2. Okay? And since there are only 2 and they are in parallel, the single equivalent will just be simply the product all over the sum. So this will be 96 over 22. And what will come out will be 4.36 ohms. So after taking the single equivalent of this one, it seems, okay, we try to remove this one now. What comes out is 4.36 ohms. Right? So actually we are moving from right to left, and the circuit now is being, what you call this, being simplified. So if we try to inspect these 2, this RE3, RE2, which is 4.36, these 2 here and these plus this 10 ohm are actually in series. So I place it here, capital letter R with the subscript E3, meaning the single equivalent RE3 will be 2 plus 4.36 plus 10. They are all in series. So the total resistance now will be 16.36. So it seems the circuit now is just be simply something like this. Right? This is 16.36 ohms. This is 24 volts. And actually, we could compute for the total current now, because we compress already the so many resistances. So the single equivalent resistance of the entire circuit now is 16.36, and the total applied voltage is 24. The total current will be 24 over 16.36. And what will come out will be 1.467 amperes. Okay, so this is 1.467 amperes, right? Well, that, I will get my eraser, guys. I'm getting my eraser. So we now know the total current. So we must have to draw again the circuits, so we could visualize what we are computing. Right? This is 4 ohms and this is 12 ohms. So we know the total current now. And to compute for this, Okay? We must have to know the voltage across AB here. If we try to compute for the voltage across terminal A and B, I mark this one as A and B. The voltage across AB will be 24 volts minus the voltage drop here minus the voltage drop here, considering this law. Okay. So we are using Kirchhoff's voltage law, meaning the summation of 24 is actually equal to the voltage drop here plus the voltage drop across AB plus the voltage drop across the 10 ohm load. Okay, so I place it here. The voltage across terminals AB will be the applied voltage 24 minus the drop here minus the drop here. The current passing here in here are actually the same, 1.467. So this is 1.47 times the quantity 2 plus 10, which is 12. And if we try to compute the voltage across AB, it is 6.4 volts, meaning the voltage here is 6.4 volts across this. Right? And this voltage here is the same as the voltage across these two here. So if we try to compute the current passing here, it should be the voltage here, okay, divided by the sum of 4 plus 12. So actually the current passing here is the one we are looking for, I, capital letter I with the subscript SC. It will be the voltage across AB all over the sum 4 plus 12. And what comes out is 0.4 amperes. So the short circuit current from step number 1 will be 0.4 amperes. Okay, it is this. Right? Step number 2. Short the voltage source and solve for capital letter R with the subscript N. If we try to short the voltage source, we short the voltage source here. So this will be gone, right? So there is no more 24 volts here. So we got the 2 ohms, 10 ohms. The middle portion is actually 6 ohms. 6 ohms. And this is still 4. And this is 12. Okay? We'll try to compute for the voltage across these terminals here, the open circuit terminal. So if we try to compute the resistance across this by using our ohmmeter, or by using it, or by solving it theoretically, we still use our knowledge of the so-called series parallel combination concepts. We start from, since we are computing for the resistance across this, we will start from the left. And these two here is in series with this 10 ohm. And I will represent that one as RE1. So that will be 2 plus 10 and that will be 12 ohm. Single equivalent of 2 and 10 will be 12 ohms. And the single equivalent of that of 2 and 10, which is 12, it will be in parallel with the 6 here. And I will represent the single equivalent of that one to be the product of 6 of 12 times 6 over 12 plus 6. And what will come out will be 72 over 18, and that will be 4 ohms. Okay? So it seems we remove this one now, we remove this one, and this is now just simply 4 ohms. Okay? After simplifying it. So if we try to compute for RL, this is gone, right? We take already the equivalent. Capital letter R with the subscript N, meaning the open circuit Norton's resistance, represented by R with the subscript N, will be the summation 4 plus 4 plus 12. They are all in series now. So I place it here. RE3 will be R sub N, the one we are looking for. So R sub N now will be 4 plus 4 plus 12. 4 plus 4 plus 12. And what will come out will be equal to 20 ohms. So this is 20 ohms. So by using Norton's theorem, the open circuit resistance for step number 2 will be 20 ohms. Okay? Step number 3, the last part. The last part is draw the Norton's equivalent of the given original circuit. And if we try to draw, like what I said from concept number, lesson number 13, which is actually the concept of Norton's theorem, the short circuit current is in parallel with Rn, okay? This is the original terminal in which the load, we are looking for the current is actually 8 ohms. Then we try to reconnect the load now. Okay? And from lesson number 13, actually I derived already the formula on how to compute for the short circuit current. It is actually given by this equation here. Okay? It will be the computed short circuit current times the open circuit resistance represented by Rn all over the sum of Rn plus RL. We know the short circuit current from step number 1. We know the value of Rn from step number 2. Still, Rn is given, RL is given. So, substituting values, the short circuit current is 0.4 amperes. And the value of the open circuit resistance using step number 2 is actually 20 ohms. This is times 20 all over 20 plus 8, or this will be 8 over 28. And what will come out is 0.285 amperes. So the current passing through this 8 ohm load here is 0.285 amperes. And if we try to complete or what you call this, compare the past solution using Thevenin's, the current is still 0.285 amperes. And again for this morning, by using Norton's theorem, the current is still 0.285 amperes. Okay, that's it guys. So for those of you who would like to subscribe to my channel, you could subscribe to my channel by going to youtube.com/@ProfDavidJ. If you want to share it, please click share. I am assuring you, you will get something from it. Okay, good morning from Los Angeles, Professor David J.